The paper title is GC eDRAM Design Using Hybrid FinFET NC-FinFET. We are two teams from the University of Notre Dame and University of California, Berkeley. I'm Ramin Rajai, a postdoc researcher at the University of Notre Dame. In this presentation, first I will provide the background, motivation of the work, and NC-FinFET compact modeling. And then I will present a hybrid FinFET NC-FinFET design technique for GC eDRAM design at the circuit and array levels. And then I will present simulation results, comparative analysis, voltage scaling for low power design. And finally, I will conclude the paper. Gain cell embedded DRAM memories or GC eDRAM eDRAMs can offer some superior advantage over the conventional SRAM arrays, including logic density, dual port operation, and performance. So we can consider GC eDRAMs as a good choice for embedded high performance and dense memories like cache memories. The main challenge with eDRAMs is data retention time. The eDRAMs encode data as the electric charge of capacitors that leak over time. So we need to refresh the state of these memories to get data valid. eDRAM cells with higher DRTs are more interesting as they need less frequent refresh, which can lower complexity and associated energy or power for refresh. In our prior work, reference 5 of the paper, we showed that eDRAM design at sub 20 nanometer is very challenging because of low DRTs we can obtain at such low technology nodes. We showed that NC-FinFET can efficiently improve DRTs. We used a 14 nanometer experimentally calibrated NC-FinFET model and showed that DRT and power consumption can be improved considerably, but at the expense of some delay overheads. In this paper, we propose a hybrid FinFET NC-FinFET design technique for GC eDRAM design to benefit from high performance, high DRT that NC-FinFET can offer, and also the performance efficiencies of FinFET. We also propose a modified circuit for a prior 40 eDRAM cell that can facilitate layout design. We also consider the array design and extrapolate the hybrid technique for the peripheral circuits, and also we explore voltage scaling considering the impacts, its impact on DRT and refresh energy. The designs that we considered in this paper are shown on the right side of this slide. Since the eDRAM cells usually employ 2 to 4 transistors to be dense and low power and high performance, so we cannot find a lot of designs, eDRAM designs in the literature. Superior work mainly work on are based on these designs. They use some minor modifications, such as using various transistors type or like hybrid P and N types, or study some effects like body biasing or different technology nodes, all aiming to result in higher DRTs. So we consider a 2 transistor cell maybe as the basic cell baseline design for eDRAMs, and also a 3 transistor cell, another 3 transistor cell, a recent 4 transistor cell that can provide a very high DRT, and also maybe the most recent eDRAM design that we presented in a conference this year. That is a 4 transistor single supply voltage that can offer a good high DRT. Our studies and contributions in this paper all are based on the NC-FinFET model that we use. This model is based on solving the LK equation, and the data is calibrated based on a device fabrication done at the University of California, Berkeley. The ID VGS and ID VDS characteristics of the design of the device and the model show that uh, they are pretty matched and show a good calibration of the model. Our simulations show that NC-FinFETs, when compared to FinFETs, improve ion over I-off ratio. They decrease I-off current, but unfortunately, they also decrease ion current by approximately 13%. So for GC eDRAM design, the reduced I-off current can help the design to obtain higher DRTs and lower power consumptions, but because of the lower and the reduced ion current, uh, the GC eDRAM designs may suffer from lower performance, more read and write delay. Now we propose a hybrid technique, hybrid FinFET, NC-FinFET design approach for eDRAM design to benefit from the potential DRT and energy efficiencies of the NC-FinFETs and still benefit from the performance efficiencies of the FinFETs. As a general rule, we propose to use NC-FinFETs for transistors on the leakage path and use FinFETs for other transistors that can affect read and write delay. We consider these rules for the five prior designs mentioned in our earlier slides. Based on the topology of the design, this design can benefit from the hybrid design solution. For the two transistor cell, we use NC-FinFETs for N1 and FinFET for N2. Capacitor node of Sn loses its stored data due to leakage currents pass mainly through N1. So when we use NC-FinFET for N1, we can reduce the leakage current and improve the DRT. And we use a FinFET for N2 that has a higher on current and can result in a faster read operation. Similarly, for the three transistor cells, we use FinFETs for pass transistors and NC-FinFET for pass transistors and FinFET, baseline FinFET for the transistors connected to the read bit line. For the 44 transistor cell, we use NC-FinFETs for N1 and N2. We examine different combinations of the transistor per our simulations using NC-FinFETs for N1 and N2, and FinFETs for N3 and N4. We showed, our simulation showed that the best DRT and performance can be obtained using this combination. In this design, when Sn is holding 1, this transistor is on, and this pull-up current can help to deal or combat with the leakage current, so it can improve DRT. When Sn is off, one leakage path is through N1 and another through N2. So using NC-FinFETs can help the device to improve for an improved DRT. We have another suggestion for this design. We propose a modified version for this design. In the modified design, we connect N1 to our read word line or RWL instead of VDD in the original design. It can facilitate the layout design. So with the new version, we do not need to wiring for VDD through the array. Our peer work, the proposed 4TSS design cannot benefit from the HP or hybrid approach, as all the transistors are cascade, and so using a hybrid approach may help the DRT when compared to FinFET implementation, whereas cannot improve the read or write delays when compared to an NC-FinFET implementation. We also consider the hybrid approach for at the array level, and we show that the peripheral read and write circuits using this hybrid approach can improve DRTs. DRT can the write circuit can effectively affect DRT in a pure work published in TVLSI. The others have proposed this circuit. This circuit applies a voltage level of VDD over 2 for the data input. This can help to improve the DRT, but this circuit suffers from a high static current and power consumption. So using a hybrid FinFET NC-FinFET approach, we propose to this circuit that is simpler and results in lower energy overhead. We show that using the proposed hybrid approach at the cell and array levels, we can improve DRT and power consumption and keep the read performance high. So let's take a look to the simulation results. For the simulations result, we use a 14 nanometer FinFET and a 14 nanometer NC-FinFET model. The supply voltage was set to 0.8, and we considered 3 types of implementations for the 2T, 3TSS, 3TC, and 4T designs, including a pure baseline FinFET or BS, pure NC-FinFET implementation or NC, and a hybrid BS-NC that we call HB or hybrid. This paper, this table compares the static power consumption. One advantage of eDRAMs over SRAMs are their much lower static power consumption. Per our simulations, the NC and HB design have improved the static power over the BS designs. So BS designs and then NC and HB designs. And the proposed HB designs offer up to 86% improvement for power efficiency when compared to the BS designs. It should be noted that the modified 4-transistor HB cell incurs a power penalty of, again, 86% when compared to the 2T transistor HB cell, 2-transistor HB cell. But we will show that as the circuit effectively improve DRT and needs less frequent refreshes, so this design will offer much more power saving, power efficiencies than the 2T cell. We compare in this slide, we compare the performance, read delay, and write delay. This figure suggests that that almost the same, that the HP designs have almost the same read delay as the BS designs, and the HP designs have a higher read performance than the NC designs, that is up to 47% improvement. Regarding the write delay, the HP designs have almost the same write delay as the NC designs, and the HP designs have a higher read delay than the BS designs, up to 49%. So the HP technique can help read delay and improves the read delay and offers a higher read delay as the BS designs, but cannot improve the write delay. Now we compare DRTs. DRT depends on the state of SN and word bit line when data is in when the cell is in holding mode or write word line is keeping 0. For when SN and word bit line have the opposite logic states, this is the worst case for DRT. For all the considered circuits, we measure the worst case DRTs, and the results show that DRT of the 2T and 3T cells when implemented using FinFET are not considerable or are very low, and actually such implementation is not feasible. But NC implementations and HP implementations can offer a good and acceptable DRTs for these compact designs, more than 2 or 3 microseconds. And regarding the 4T cell, even when implemented using FinFET, it can offer a high DRT. So the HP designs have almost the same DRT as the NC designs, and up to 31 times longer DRTs than the BS designs. We also considered process variation, process and voltage variation. This study actually is important, as can help us to consider the worst case process and voltage conditions in choosing an appropriate or safe refresh frequency. For example, for the 2 transistor cells, the results reveal that the retention time, DRT, can vary from 2 microseconds to 4 microseconds. And for the 4 transistor circuit, can be from 200 microseconds to even more than 1 millisecond. And now in final, we explored voltage scaling, considering its impact on DRT and refresh energy of the proposed hybrid NC-FinFET and FinFET eDRAM designs. In this study, we considered the HP designs as well as the BS 4 transistor cell, as they offer high DRTs. Voltage scaling is a well-known technique in low power design. Voltage scaling in eDRAM design is important for study, as in one hand, voltage scaling decreases the refresh energy needed for a single refresh, but it decreases the DRT and hence increases the refresh rate. These two effects would not be the same and cancel each other, so we compared DRT and refresh energy scaling at a scaled supply voltage at different supply voltage from 0.4 to 1 to answer the following questions. And the questions are: for a given design, what is the optimum supply voltage for a low power design? And among the considered GC eDRAM cells, which design has the lowest power consumption? This figure compares DRT versus the refresh energy, or refresh energy versus DRT for different designs in different supply voltage levels. And to identify the design with the lowest energy, we propose energy cost function that is given by this formula. ECF is energy cost function, DRT is DRT, RF is refresh energy. And here we compared the ECF of the designs, and the results suggest that the 4 transistor designs, the 4 transistor BS and hybrid implementations, can offer lower ECFs than the compact 2 transistor and 3 transistors, as they effectively improve DRT and needs for lower refresh frequencies. Another notable thing is the modified 4 transistor HP cell offers a low ECF at 1 volt, where it can offer a high performance at this voltage. So in conclusion, in this paper, we proposed we studied GC eDRAM designs at deeply scaled 14 nanometer technology node based on FinFET and NC-FinFET devices. We showed that we can benefit from a hybrid FinFET and NC-FinFET design technique to offer the DRTs and energy consumptions of NC-FinFET, and also benefit from performance potentials of FinFET. We considered 4 prior designs and showed that using the proposed hybrid approach can offer up to 31 times longer DRTs, up to 7 times lower power consumptions and up to 2 times faster read operations. We also voltage scaling was also studied in this work, and our simulation results suggest that the proposed modified 4-transistor HV cell has much lower refresh energy, up to 370 times lower than the other functional equivalents. Thank you.